Today, I'll share our work on providing completion time predictions to users and making this a first-class concept in today's cloud. So this is joint work with my colleagues from Tufts University. We are inspired by real-world systems, most of which provide their users with a time estimate. For example, when you order something from Amazon, Amazon will tell you when your parcel will arrive. Similarly, when you booked a ride from San Jose Airport to the hotel, Uber must have informed you when your driver would be arriving. So these predictions help improve the service quality. In this work, we ask the question of whether the cloud can offer a similar functionality. Now, by that, what we mean is when a user submits a job to the cloud should inform the user when their job will complete. This notion can be applied to different contexts, and one important kind of cloud context is a multi-tenant GPU cluster. These clusters are growing in popularity due to the emerging demand of AI applications. Meta, for example, just announced that they'll be increasing their fleet of GPUs to 600,000 by the end of this year. In this setting, different users bring their machine learning workloads, and a scheduler arbitrates resource access across these users. Studies have shown that these clusters are highly loaded, and predictions, for instance, can improve experience in such settings, provided that these predictions are reliable. So what impacts the reliability of these predictions? Several system factors can make these predictions unreliable. For example, you can have failures, you can have stragglers, or downright outages. In this work, we are focusing on the unpredictability that stems from the scheduling mechanism used by the cluster. And in particular, due to the preemptive versus non-preemptive nature of the allocation policy used by the scheduler. Real-world systems are non-preemptive in nature. By non-preemptive, what we mean is that future jobs, for example, customers, do not impact the completion time of existing ones. In this simple example over here, we have a customer with size 10 that arrives at a queue, a FIFO queue, and the system is going to inform the customer that you will finish at time 10. And when a future customer comes in of size 5, let's say, the future customer is going to strictly sit behind the existing one, not impacting the completion time of the one that was already in the queue. This is what we mean by non-preemptive systems, and they can offer predictability. However, such systems are also well known to suffer from performance practical issues due to, for example, head-of-line blocking. To counteract these practical issues, cloud systems employ preemptive scheduling policies. And typically, they employ unbounded preemption. For example, they may do so in order to prioritize jobs based on their size, in order to minimize job completion times, or to share resources across jobs in order to implement fairness measures. And this can cause unpredictability. Alluding to the same example, you have a customer that's already in the queue, and a future arrival can result in the time of the existing customer changing. If the policy is shortest job first or fair share, the existing customer's time is going to be stretched from 10 units to 15 units, an increase of 50%. So this is what we mean by prediction error and unpredictability. So this analysis reveals that there's a trade-off between predictability and practical goals. Existing solutions lie at extreme ends of this trade-off space. So FIFO is predictable, but suffers from practical issues. And on the other extreme, you have schemes like fair share and shortest job first. Now, our experiments reveal that FIFO, for instance, can suffer from a 10x performance cost, while preemptive schemes can have more than 100% prediction error on average. So the key question that we want to answer with this work is, can we offer predictability while balancing other practical objectives? And the answer to this is predictability-centric scheduling. So PCS is a generic job scheduling framework, and we make contributions on the algorithmic side as well as system side of things. On the algorithmic side, we use weighted fair queues as a building block because weighted fair queues provide bounded preemption, and more importantly, they provide control over the preemption used. Different weighted fair queue configurations can achieve different trade-offs. We couple weighted fair queues with the simulation-based search strategy. The simulation-based search strategy offers a practical way to find different configurations that can realize different trade-offs. And we employ heuristics to make this search efficient. And finally, PCS offers a high-level interface that operators can use to navigate this trade-off space. And the key idea over there is that we reduce the trade-offs to Pareto optimal choices that the operator can then choose from. So for the rest of the talk, I'm going to motivate supporting PCS for ML workloads. I'll then move on to the design, in particular focusing on our use of weighted fair queues, our search strategy, and the high-level interface, and finally share some evaluation results with you. So firstly, why provide predictions for ML workloads? There's a large body of work in recent times that have shown that GPU cluster users suffer from frustration-related issues. And in particular, the frustration can reach a point where they end up quitting the shared setting. Similarly, another study reveals that GPU cluster users are actively making these predictions themselves. And these user-generated predictions can be off by more than 100%. The same work, interestingly, also says that predicting a completion time of a job is infeasible because of the scheduling algorithm and the dynamic state of the cluster. So let's see what makes it feasible in the context of ML clusters. So the first thing is, in order to generate a reasonable prediction for a job, I need to know the sizes of individual jobs. Luckily, ML workloads are amenable to such a setting because an ML job's demand function is either known or can be reliably estimated. The demand function is a mapping from resources allocated to a job to its execution time. And this is necessary to generate a reasonable prediction. And this facet has been leveraged by prior scheduling systems as well. However, we still need to figure out how to make this prediction accurate because it does depend on the scheduling algorithm used. A related issue is that while the demand function is known, it can be complex. And this is because ML jobs exhibit sublinear throughput scaling. For instance, the graph over here shows on the x-axis, GPU is allocated to a job and the throughput on the y-axis. So it does not follow a linear scaling trend. And thus, it's unclear how to allocate GPUs to such jobs. Should it be the maximum, should it be the minimum, or somewhere in between? So I'll now talk about the design and how we incorporate and address some of these challenges. So recall that the goals of our system is firstly to offer predictability, and secondly, to balance other objectives. Weighted fair queues help us address and achieve these goals. In weighted fair queues, different jobs are mapped to different queues. Jobs within a queue are processed according to FIFO order. Each queue gets a guaranteed resource share, which is the queue's weight, and the number of queues, their weights, and the job mapping criteria are all configurable parameters of the system. The key takeaway is that the combination of guaranteed resource share and FIFO scheduling within a queue bound the prediction error, while weighted fair queue also provides the necessary baseline flexibility to achieve some of the goals. So, weighted fair queues allow us to span the scheduler space. The core contribution of our work is to intelligently configure weighted fair queue parameters to approximate different schedulers in the design space. For instance, you can have a weighted fair queue with a single queue, and that essentially behaves as a FIFO scheduler. Similarly, by mapping each job to its own queue and assigning a significantly higher resource share to the queue with the smaller jobs, you can approximate shortest job first. And with a slightly different weight assignment, the same queue can also approximate fair share. So the key takeaway is that weighted fair queues can approximate extreme points in the design space and potentially could also offer intermediate points if they're configured correctly. So this is a big if, which I'll come to in a bit. One optimization that we make with weighted fair queues is to address the head-of-line blocking problem. Since we have FIFO within a queue, simply mapping different jobs to queues will still not resolve the head-of-line blocking problem. So in this work, the way that we augment weighted fair queues is to map similar sized jobs to the same queue. And this can be achieved by having an appropriate number of queues with different thresholds. The second optimization that we make to weighted fair queues is to handle complex demand functions. So recall that ML jobs exhibit sublinear scaling, and a key result from scheduling theory is that schemes like shortest job first are only optimal if the job's throughput scales linearly with respect to allocated resources. But this isn't the case for ML jobs. And prior work, which aggressively prioritizes efficient jobs, can lead to unpredictability, as our results will show later. So we need to have a slightly different mechanism. The key idea is, in this setting, we cap a job's maximum possible allocation. And more formally, we compute a job's efficiency as the ratio between its throughput the ratio between its throughput and the number of resources allocated to it for different allocations. And then we cap the maximum allocation to K such that the efficiency is at least above a certain threshold. This efficiency threshold is also a configurable parameter of our system, and intuitively, a higher threshold means that there's a higher chance of GPUs being taken away from that job. So let's look at a simple example of, let's say, 8 GPUs and a threshold of a minimum efficiency threshold of 0.75. So I'm using the same throughput characteristic that we saw earlier, where a job can be allocated different GPUs and observes different throughput. So this follows a sublinear trend, and for each allocation, we've also computed the efficiency at that allocation point. So based on the minimum threshold, we will cap the job's maximum allocation to 4 GPUs. And everything that's more than 4 GPUs is purely opportunistic. So when the job is the only job in the system, it will get access to all of the GPUs. But as soon as a new job comes in, the extra GPUs will be freed and allocated to the job that's next in line. So it's strictly, the allocation is freed and strictly follows like a FIFO order. So the takeaway is that this conservative strategy of incorporating efficiency trade-offs some predictability for additional performance. So now, these different parameters of the weighted fair queue, the number of queues, the queue weights, the efficiency threshold are all configurable parameters, and they jointly influence the trade-offs that we want to achieve. In the general setting, it's hard to reason about the combined impact of these different configurations. We take an empirical approach. So we empirically determine the impact of different parameters that are chosen. We sample different weighted fair queue configurations from the search space, different number of queues, weights, etc. And then we pass it to a simulation-based strategy. So the simulator is going to try out these different configurations in parallel on the collected workload, and it's going to come up with a ranking for different weighted fair queue configurations. In this example, we're interested in, let's say, the average job completion times and the average prediction error achieved by each weighted fair queue configuration. And once we have this ranking, we can simply discard those configurations that are not Pareto optimal. And we keep on repeating this process until we converge. Now, the search space can be combinatorial in nature and very large. The naive parameterization will result in significantly higher number of parameters that we would want to search over. Roughly, it's going to be like a product of the number of queues, thresholds for each queue, weights, etc. Our idea is to reduce and make this more efficient, and the key bit is that we want to increase the likelihood of a random weighted fair queue sample being Pareto optimal. And we do this by intelligently parameterizing the weighted fair queue configurations. So one heuristic that we use is to, instead of trying out arbitrary weight combinations, we use exponentially shrinking weights. The heuristic stems from the fact that assigning exponentially lower weights to queues that have longer jobs generally tends to improve performance. And formally, the weight of the kth queue is proportional to the negative exponential of the index of the queue times capital W. So now capital W jointly controls the weights for all queues. And intuitively, a larger W means that you want to be more aggressive in shrinking weights for queues that have longer jobs, while a smaller W starts to approximate a fair division. We also have other heuristics that we discuss in the paper. Now, we want to simplify navigating this trade-off, and the issue is that the exact trade-off is unknown a priori. The trade-off is highly workload dependent, and this means we can't say something like, have 10% error, but it's okay to take a 1.5x performance hit. We propose a high-level interface which allows operators to specify high-level objectives, and PCS provides Pareto optimal choices. So the supported objectives are prediction error, job completion times, and unfairness. So operators use this interface to specify these objectives. The solver solves and searches over weighted fair queues, presents the Pareto frontier, and then the operator can simply choose from this front. Now I'll share some key evaluation results. So there are 3 key questions. How does PCS fare under realistic settings? Can the simulation-based search strategy find the Pareto frontiers? And how effective are the heuristics in improving the efficiency of the search? So for the first result, we set up a small-scale testbed of 16 GPUs on an AutoML style workload where different jobs spawn multiple DNN trials, and we compare PCS with AFS, which is a performance baseline, a recently proposed ML scheduler, and our predictability baseline is FIFO. So this result shows, this graph shows the trade-off achieved by PCS. On the x-axis, we have the average prediction error, and on the y-axis, we have the normalized average job completion time. So PCS is able to achieve 30% less prediction error while being within 5% of the optimal scheme. And if we zoom in, this is the CDF of the prediction error for all jobs, and we see that PCS is able to reduce the prediction error by 80% for 95% of the jobs. For now, we also run the simulation-based search strategy across different realistic workloads, and we can see that our simulation-based search strategy is able to find the Pareto frontier, and each point is basically a weighted fair queue configuration that achieves that trade-off. And finally, we look at the effectiveness of our heuristic by tracking the number of Pareto points that are discovered as a function of the evaluation budget. So we can see that for conservative evaluation budgets, the heuristics can help in discovering more of the Pareto front. So that's all. In summary, we first talked about how providing predictions is a useful thing to improve user experience in shared settings. And we talked about the predictability versus practicality trade-off, and then how weighted fair queues can help address this trade-off, coupled with a simulation-based search strategy to navigate and search different points, and a high-level interface that can allow operators to choose different points in the trade-off space. Our evaluation results show that PCS is able to achieve low prediction errors while being competitive with other schedulers. So that's all I have for today. Thank you.